Hello everyone! This video is entitled Understanding Chemical Equations. In this lecture, I will describe the relationship between energy and matter, explain how exothermic and endothermic reactions differ from one another, distinguish between chemical equations, word equations, and skeleton equations, and explain how to balance chemical reactions. Okay, let's get started.
Energy, as we know, can be transferred from one substance to another. However, it can get quite complicated when it comes to measuring or understanding the transfer of energy between substances. In order to interpret energy changes, scientists must clearly define what part of the universe they are dealing with. Now, I know it sounds odd that scientists make reference to the entire universe when discussing the energy change between two substances. But you need to keep in mind that when particles in a reaction exchange energy, they are simultaneously transferring energy to and from the container housing the reaction, which in turn is releasing energy to or absorbing energy from the air around it. And this chain of events continues on and on without end. And so, to focus attention on the chemical interaction within the chemical reaction, scientists have divided the universe into two categories, the system and the surroundings. The system is defined as the part of the universe that is being studied and observed. The surroundings are everything else in the universe. For a chemical reaction, the system is made up of the reactants and products. Reactants are pure substances that undergo chemical changes, and the products are pure substances formed by chemical changes. The properties of the products are always different from the properties of the reactants. The laws of matter and energy provide substantiation for the distinction scientists make between a system and its surroundings. The idea that energy will be transferred from one substance to another endlessly throughout the universe stems from the law of conservation of energy. The law states that in a physical or chemical change, energy may be converted from one form to another, but the total amount of energy remains constant. Take the movement of an electrical fan, for example. When the fan is turned on, the motor begins to heat up, which means that electrical energy is being converted into heat rather than being used to turn the blades. This is a perfect example of energy conservation. At first glance, it would seem that the electrical energy is lost or destroyed. But actually, it is merely being converted into a different form of energy that is then transferred into the surrounding air. Now, of course, this relates to chemistry because all chemical reactions involve the release or absorption of energy. The second law that you must be aware of is the law of conservation of mass. Similar to the law of conservation of energy, this law states that in any chemical reaction, the mass of the products created is always equal to the mass of the reactants. Basically, it states that matter cannot be created nor destroyed. When a log burns away in a flame, for example, the matter within the log is not destroyed, but rather converted into other forms of matter, such as ash, carbon dioxide, and water vapor. Chemical reactions can be classified as either endothermic or exothermic. When heat or energy is absorbed by a system from the surroundings, the reaction is considered endothermic. A great example of this would be the cooking of an egg. You can obviously tell that a raw egg undergoes a chemical change while it's being cooked because of how different it looks right before it's consumed. In order for that reaction to occur, energy in the form of heat needs to be added, making the cooking of an egg an endothermic reaction. At a molecular level, these reactions need energy input because there is more energy required to break the bonds of the reactants than there is energy released when new bonds are formed in the products. It is very important to remember that when bonds are formed between atoms, energy is always released. The more stable the bond being formed, the more energy there is released. And so, if a reaction is endothermic, then we can assume that the products formed are not as stable as the reactants being broken. We know this because there is more energy being used to break the reactants than there is energy released when the products are formed. Now, in contrast, when heat is released by a system into the surroundings, the reaction is considered exothermic. A great example of this would be a thermite reaction. This is a reaction between raw aluminum metal and iron 3 oxide to produce molten iron and aluminum oxide. This reaction is so exothermic that it reaches temperatures greater than 5,000 degrees Celsius, close to those on the surface of the sun. At a molecular level, these reactions need very little energy input because there is more energy released when new bonds are formed in the products than there is energy required to break the bonds of the reactants. In this situation, the products formed are more stable than the reactants being broken. Chemical reactions are expressed as chemical equations. A chemical equation is a representation of what happens to the reactants and products during a chemical change. There are three forms of chemical equations. The first is a word equation. Word equation shows the names of the reactants and the products with an arrow dividing the reactants on the left from the products on the right. The example we have here is a reaction between hydrogen and oxygen to form water. The second type of chemical equation is a skeleton equation. Skeleton equations replace the names of the reactants and products with the chemical formulas. And so again, here we have the chemical formula for hydrogen reacting with the chemical formula for oxygen to form water. The third type of chemical equation is a balanced chemical equation. Here, we add coefficients in front of the skeleton reactants and products to balance the equations. Several different methods for balancing chemical equations have been created over the years. I personally have found none of these methods useful. So I have created my own set of balancing rules. There are 4 rules in total. The first, if the same polyatomic is on both sides of the reaction arrow, balance the polyatomic first as one unit. The same rule applies if you have more than one kind of polyatomic in the reaction. Rule number 2. Balance the element whose quantity has been changed in step 1. Then go back to the beginning of the reaction. Rule number 3. If you encounter an odd number of atoms for the element you are trying to balance, and it is difficult to convert to an even number, skip that element. Balance it last. And rule number 4. If you have to balance an odd number of atoms for an element, with a fraction, multiply the whole reaction by 2 to get rid of the fraction. Now, some of these rules may seem a little cryptic until you start doing some practice questions. So let's jump into some questions together to see how these rules can be applied. For my first example, I have a reaction with 2 different types of polyatomic ions. I have a carbonate ion here, I have a phosphate ion here, and I have another phosphate ion here in my product. Now, you can see that I have phosphates on both sides of my reaction arrow. And so let's refer to rule number 1. Rule number 1 states that if the same polyatomic ion is on both sides of the reaction arrow, you balance the polyatomic ion first as a single unit. The same rule applies if you do have more than one kind of polyatomic ion in the reaction. However, that's only the case if the other polyatomic ion is on both sides of the reaction arrow. And so if you take a look at carbonate, carbonate is only on one side of the reaction arrow. It does not exist in the product side. Now, although carbon dioxide looks like carbonate, it is not carbonate. Because of that, I cannot treat it as a single unit. Looking at my phosphate ions, I have one phosphate ion in my reactant side, and I have one phosphate ion in my product side. And so in fact, the phosphate ions are already balanced. And so there's nothing left for me to do than to move on to rule number 2. Now, rule number 2 states, balance the elements whose quantity has been changed in step 1. And so in fact, because I didn't change anything with my phosphate ions or any of the other elements, I can then move to the beginning of my reaction. At the beginning of my reaction, I have 1 potassium on the reactant side, and I have 2 potassium on my product side. And so the fastest way to balance that is to add a 2 in front of my potassium. Now by adding that 2, I've essentially changed the amount of hydrogen, carbon, and oxygen. But we're going to do this step by step. And so the first thing I'm going to focus on is the hydrogen. And so now I have 2 hydrogen plus 3 hydrogen. Of course, you have to keep in mind you're taking the total amount of hydrogen on the reactant side and comparing it to the total amount on the product side. And so I have 5 hydrogen on the reactant side, and I only have 1 plus 2, 3 hydrogen on the product side. And so the fastest way to convert these 3 hydrogen into 5 hydrogen is to add a 2 in front of this hydrogen. By doing this, I now have 4 plus 1 give me 5 hydrogen. Now, by changing the amount of hydrogen, I've now changed the amount of oxygen. And so you're doing it stepwise. You don't go back to the beginning. You basically work through the reaction the way the balancing takes you. And so here I've changed the amount of oxygen. And so I have 2 oxygen plus another 2 oxygen. That's 4 oxygen. Now, I know you're looking at the oxygen in phosphate, but again, remember, we balance the phosphate ion as a single unit. And so we don't look at these oxygen anymore. This is considered balanced. And so now we're looking at the oxygen here. We have 4 oxygen. And on this side, we have 6 oxygen. And so the quickest way to make 4 into 6 is to add a 2 in front of the carbon here. And now we have 4 oxygen plus 2 oxygen gives us 6 oxygen. And that balances out with the 6 oxygen on the reactant side. And in fact, by doing that, we also balance the carbon inadvertently. So now we have 2 carbon here and we have 2 carbon here. Now, if we did a quick look, 2 potassium, 2 potassium. We have 2 plus 3, that's 5 hydrogen, and we have 5 hydrogen. We have 2 carbon here, and we have 2 carbon here. And of course, we have 6 oxygen and 6 oxygen. And the phosphate has remained unchanged, 1 and 1. And so we have a balanced chemical equation. On to our second example. Now, our second example again shows 2 different types of polyatomic ions. We have the ammonium ion here, and we have the phosphate ion on both sides. Now, because the ammonium ion is only on one side of the reaction arrow, we cannot treat it as a single unit, but we can treat the 2 phosphate ions as a single unit based off of rule number 1. Looking at the phosphate ions, I know that I only have 1 phosphate ion on both sides, and so again, phosphate self-balances. So it brings us to rule number 2. Rule number 2 states that we should start at the beginning. And so I have 3 nitrogen on this side of the reaction arrow. And remember, the 3 comes into the bracket. And so the easiest way to balance the nitrogen on this side is to add a 3. By doing that, I changed the hydrogen. And so you can see here that 3 times 3 is 9. 9 plus 2, that's 11. So I have 11 hydrogen on this side. Taking a look at this side, I have 4 times 3, that's 12.
plus 1, that's 13 hydrogen. And so I've arrived to an issue here. I have an odd number and I have another odd number, and I'm trying to balance them, and that can prove very difficult. That brings us to rule number 3. If you encounter an odd number of atoms for an element that you are trying to balance, and it is difficult to convert to an even number, skip that element, balance it last. So we're going to skip hydrogen and we're going to move on. If we take stock of what we've done so far, we've balanced the nitrogen, we've skipped the hydrogen, the phosphate has been balanced, and so that brings us to sodium. I have 1 sodium on this side of the reaction, and here I have 3 sodium. And so I add a 3 to this sodium, and now I've changed the number of oxygen. So I have 3 oxygen on this side. Remember, I'm ignoring the 4 oxygen in the phosphate because I'm treating phosphate as a single unit, and that's the beauty of treating these polyatomic ions as single units. I can just ignore them. And so I have 3 oxygen here. How many oxygen do I have here? Well, I have 1 oxygen right there. Again, I'm ignoring this phosphate. Best way to balance that is to add a 3, and so now I have 3 oxygen. But again, by doing that, I've changed the amount of hydrogen. But that's okay because we skipped hydrogen. So now let's try to balance hydrogen. It's the last element we have to balance. 3 times 3, that's 9, and 3 times 2, that's 6. 9 plus 6 is 15, and so now I have 15 on this side. Here I have 4 times 3, okay, that's 12, plus 3, that's 15, and so now I've inadvertently balanced the hydrogen just by leaving it to the last step. That's why it's so important to follow these rules step by step. If I tried to balance the hydrogen in the middle of my process, it would prove very difficult to do and it would be very time consuming. And so by leaving it to the end, I've actually inadvertently balanced it. So that brings us to our next question. Again, our next question has quite a few polyatomic ions just at first glance. We have 2 different types of polyatomic ions. We have a nitrate on both sides of the reaction arrow, and we have a carbonate on both sides of the reaction arrow. So again, rule number 1 states that if you have them on both sides of the reaction arrow, you can balance them as a single unit. The same rule applies again if you have more than one type of polyatomic ion. I know that I have 1 carbonate on both sides of the reaction arrow, but in the case of nitrate, I have 2 on the reactant side and I only have 1 on the product side. And so the quickest way to balance that is to add a 2 in front of that compound, and now I have 2 nitrate. But again, I've changed the number of sodium. Rule number 2 states that if I've changed the number of elements in step 1, I need to balance that element. And so because I have 2 sodium here, and I have 2 sodium here, I'm actually balanced. And so let's take stock of this reaction now. So I have 1 calcium, and I have 1 calcium. I have 2 nitrate, I have 2 nitrate. I have 2 sodium, 2 sodium, 1 carbonate, and 1 carbonate. And so just by treating my polyatomic ions as single units, I've actually completed the balancing of this reaction. And so it brings us to our next reaction. You can see how by following these steps, you end up going very quickly through the balancing of quite complicated reactions. With our next example, we again have polyatomic ions. The polyatomic ions that we have on both sides is sulfate. So we have sulfate in the reactant side, we have sulfate in the product side. We have a hydroxide on one side, and we have a hydroxide on the other. First thing I'm going to do is I'm going to try to balance my sulfate. I have 3 here, and I have 3 here. Now, there's 2 ways of doing this. You could immediately place a 3 in front of this sodium here to balance out the hydroxide, which would be perfectly okay. And if you did that, it would take you down a very similar road that I'm about to go down. Or, because I balanced this sulfate, I can just then balance the sodium that I've changed. And so because I have 6 sodium now, and I only have 1 sodium here, I can just place a 6 right in front of sodium. And so now my sodium are balanced. I've changed the amount of hydroxide, and so I have 6 hydroxide, and I only have 3 hydroxide here, and so the best way to balance that is to multiply it by 2. And so now I have 6 hydroxide. And by doing that, I've balanced my chromium, and I've balanced my chromium. Okay? And so there's two ways of doing that. If I did it the other way, and I placed a 3 here, then you would see that I would have 3 sodium, and I would have 6 sodium, and so I'd have to change that 3 to a 6, and then I would add the 2. And so it just adds an extra step, but either way you would get the right answer. Okay, and so for our next example, I have a nitrate ion on one side, and I have a nitrate ion on the other. Now, I will tell you just at a quick glance, this is going to be a little bit more complicated, and you'll see why in a second. So first thing I'm going to do is I'm going to balance my 2 polyatomics as a single unit, following rule number 1. And so I'm going to add a 2 in front of this compound, and by doing that, I now have 2 nitrate and 2 nitrate. What I've changed is the number of hydrogen. So now I have 2 hydrogen on the reactant side, and I have 2 hydrogen on my product side, which is balanced. I can skip the nitrate, it's already balanced. I go to my copper, I have 1 copper and 1 copper. And so now I'm left with this nitrogen dioxide. Now, the difficulty here is that I already balanced my nitrate, and by balancing my nitrate, I've balanced my nitrogen. But have I really? No, I haven't, because of this nitrogen in the nitrogen dioxide. And so I actually have to forgo rule number 1, and this is one of the very rare exceptions because I have a nitrogen that stands alone here. And so I actually have 3 nitrogen on this side, and I have 2 nitrogen on this side. Now, by balancing my nitrates as a single unit, I still can keep this 2. It's a great starting point for balancing out this reaction. And so how do I make 3 balance out with 2? Well, the fastest way to change this odd number to an even number is to add a 2 in front of it. So now, instead of having 3, I have 4 nitrogen. And so 2 nitrogen here and 2 nitrogen in my nitrate, and I have 2 nitrogen in this compound. So what I'm going to do is I'm going to change this 2 to a 4, and now I have 4 nitrogen. By doing that, I've changed the number of hydrogen, and so I'm going to place a 2 in front of this hydrogen here, and now I have 4 hydrogen. And so let's take stock of what we've done. I have 4 hydrogen, I have 4 hydrogen, 4 nitrogen, 2 and 2 makes 4 nitrogen. I have 12 oxygen, and here I'll have 6 plus 4 plus 2 gives me 12. And I have 1 copper and 1 copper. And so that reaction is balanced, which brings us to our next one. Now, this next one does not have a polyatomic ion. And so what we're going to do is we're going to start directly from the beginning. We have 4 carbon, and we have 1 carbon. And so I'm going to place a 4 in front of that carbon. By doing that, I've changed the number of oxygen. And so I have 8 oxygen plus 1, that's 9 oxygen, okay? Now I have 9 oxygen and I have 2 here. I'm going to skip that, and the reason why is because of rule number 3. And so just to remind you, rule number 3 states that if you encounter an odd number of atoms for an element that you are trying to balance, and it is difficult to convert to an even number, you skip that element and balance it last. And so because I have 9 oxygen on this side and I have 2 on this side, I'm just going to skip the oxygen. So I'm going to go directly back to the beginning. So I finished my carbon. Now I have 10 hydrogen and I have 2 hydrogen here. I'm going to add a 5 in front of it to make it 10. And so by doing that, I've actually changed the oxygen again, which is a good thing because I left it to the end. So let's see if it's self-resolved. So I have 8 plus 5, and that gives me 13. Now 13 and 2, that did not resolve my problem. So the quickest way to balance this is to think, what can I multiply by 2 to give me 13? And so 6.5 multiplied by 2 will give me 13. But I know what you're thinking. You're thinking, how is it possible to have a fraction as a coefficient? And you cannot. And so that brings us to rule number 4. If you have to balance an odd number of atoms, for an element with a fraction, you multiply the whole reaction by 2 to get rid of the fraction. And so what I'm going to do now is I'm going to multiply the whole reaction by 2, and by doing this, I get rid of my fraction, and now I've balanced my chemical equation. That brings us to our last example, and I know what you're thinking. You're thinking, could you go over that again? Not to worry, this example has something very similar happening in it. Here you can see I have 1 iron, 2 sulfur, 2 sulfur. I have 2 chlorine here, but on this side you can see that I have 3 plus 2, that's 5. And so I'm stuck now. I can't leave chlorine to the end because it is the end. I need to balance this odd number with an even number. And so I have 5 chlorine and I have 2 chlorine. What can I multiply by 2 to give me 5? Well, the fraction or the decimal I can use is 2.5. But again, rule number 4 states that if I have a fraction, I have to multiply the whole reaction by 2. So if I multiply this reaction by 2, I change my coefficients, and now I've gotten rid of that fraction. And now my reaction is balanced. And that concludes the examples for balancing chemical equations. Has a chemical change taken place? One of the greatest obstacles students face in a laboratory setting is identifying if a physical change or a chemical change has occurred. Remember that physical properties can be determined without altering the identity of a sample. However, chemical properties involve a chemical change. The only way you can identify chemical properties is after a reaction has occurred. If a sample of matter breaks down or reacts with another substance, a new substance will be produced. And because of that, you will have no more of your original substance remaining. It may be very difficult to determine if a change is physical or chemical. The states of matter can be used to help determine if a reaction has taken place. Now remember, substances can be solid, identified with S, liquid, identified by L, gaseous, identified by G, or aqueous, identified as AQ. Aqueous, again, is the term applied to solutions that have a compound dissolved in water. If a solid or a gas is produced when two substances are mixed, a reaction has most likely occurred. A precipitate is a solid formed by a chemical reaction between two aqueous salts. Now, how this occurs will be further explained in later lectures. Here I'll provide a checklist of observations that you can use to determine if a chemical change has occurred. If you make 2 or more of the following observations, then a chemical change has probably taken place, and a chemical reaction has occurred. First, determine if heat is absorbed or produced by the reaction. If so, then the reaction is either exothermic or endothermic. Then look to see if grains of solid precipitate have formed in the liquid, or if a new color appears. Are gas bubbles formed in the liquid? Is there a change in odor? Did the starting material you had become used up? Did the starting color disappear? If 2 or more of these observations can be made, then you can rest assured that a chemical change has taken place. And with the conclusion of this slide, I have concluded this lecture and this package. I hope you understood everything I discussed today. Thank you for listening. All the best.